Nomenclature of fused and bridged fused ring systems. Synopsis. These recommendations constitute a comprehensive documentation for naming fused ring systems and bridged fused ring systems. It expands and extends the recommendations given in Rules A21, A22, A23, A34, B3 of the IUPAC Nomenclature of Organic Chemistry, sections A, B, C, D, E, F and H from 1979, and Rule R 2.41 of A Guide to IUPAC Nomenclature of Organic Compounds from 1993. Any ring system with two or more rings ortho or ortho and perifused together may be named by these recommendations. Two rings which are orthofused together have only two atoms and one bond in common. The nomenclature of spirosystems and von Baer nomenclature will be considered in separate recommendations. Introduction. The general principles for naming polycyclic fused ring systems were proposed by Patterson. These proposals were developed by a joint committee of the American Chemical Society and National Research Council and were approved by the IUPAC Committee on Organic Nomenclature before publication. When sections A and B of the Nomenclature of Organic Chemistry were prepared, this technique for naming polycyclic fused ring systems was adopted. Chemical Abstracts Service has developed this method to cover the more complex examples encountered in its work. These extensions were documented in the Ring Index and in Chemical Abstracts, while additions to the Ring Index were listed at first in just Chemical Abstracts and then in the Parent Compound Handbook. They are now listed in the Ring Systems Handbook. Some long-established names used by CAS are retained by them, although they would not be so named today. Beilstein too has had to extend and develop fusion nomenclature. This document has been prepared from the sources mentioned above, and material from the Chemical Abstract Service Substance Name Selection Manual. Assistance by CAS staff members is gratefully acknowledged. Differences between the recommendations in this document and current CAS or Beilstein practice are indicated where appropriate. Basic techniques for naming polycyclic fused ring systems are considered in a number of places in the 1979 IUPAC rules. For hydrocarbons, rules A21, A22 and A23 cover the fused ring parent hydrides, which may then be used for the names of bridged systems. Heterocyclic examples are named using the extended Hunch-Widman system and selected trivial names for heterocyclic components. Details of the fusion procedure are given in Rule A21.5 and B3. Replacement nomenclature is described in Rules B4, B6 and D1.6. This document provides a unified treatment of heterocyclic and hydrocarbon polycyclic fused ring systems with recommendations for the naming of complex examples not covered by the 1979 IUPAC rules. All names are for fused ring systems with a maximum number of non-cumulative double bonds, even though the system may only be known in the form of a partially or fully hydrogenated derivative. Structures in this document are drawn as far as possible with undistorted rings. It should be noted that the use of distorted ring shapes is only necessary for the orientation of ring systems prior to numbering the system. In this document, no restriction is placed on when fusion nomenclature may be applied. Previously, it was restricted to systems which contain at least 2 rings of 5 or more members.
FR1 Definitions. FR 1.1 Fusion. Fusion nomenclature is concerned with a 2-dimensional representation of a polycyclic ring system with the maximum number of non-cumulative double bonds. In addition, this system may be bridged or involved in assemblies or spiral systems not covered by these rules. For ring systems, any ring fused to other rings on all sides must be itself named, i.e. it is not treated as a whole. For nomenclature purposes, 2 rings which have 2 atoms and 1 bond in common may be regarded as being derived from the 2 rings as separate entities. The process of joining rings in this way is termed fusion. FR 1.1.1 Orthofused. 2 rings that have only 2 atoms and 1 bond in common are said to be orthofused. FR 1.1.2 Ortho and perifused. In a polycyclic compound, a ring orthofused to different sides of 2 other rings that are themselves orthofused together, i.e. there are 3 common atoms between the first ring and the other 2, is said to be ortho and perifused to the other 2 rings. Phenylene is considered as being composed of 3 benzene rings, each of which is ortho and perifused to the other 2. FR 1.1.3 Fusion atom. Any atom of a fused ring system which is common to 2 or more rings is termed a fusion atom. FR 1.1.4 Peripheral atom. An atom that forms part of the outer perimeter of a fused ring system is called a peripheral atom. FR 1.1.5 Bridgehead atom. An atom of a fused ring system to which a bridge is attached is called a bridgehead atom. FR 1.1.6 Interior atom. Any fusion atom which is not a peripheral atom is termed an interior atom. FR 1.2 Fused ring system. A system where each bond is part of a ring, where each ring is orthofused or ortho and perifused to at least 1 other ring, and where no bond is common to more than 2 rings is termed a fused ring system. FR 1.2.1 Bridged fused ring system. A ring system where some of the rings constitute a fused ring system and the remaining rings are created by 1 or more bridges is termed a bridged fused ring system. FR 1.2.2 Multi-parent name. A fused ring system name which is constructed using an inter-parent component and 2 or more identical parent components is called a multi-parent name. FR 1.2.3 Multiplicative prefix name. A fused ring system name which is constructed using 1 or more multiplicative prefixes di, tri, etc. or bis, tris, etc. to indicate multiple occurrences of the attached components is called a multiplicative prefix name.
FR 1.3 Components of a fused ring system. Allowed fusion components are rings or ring systems which can be named without the application of any fusion nomenclature principles. Fused ring systems which do not have such a name are named by joining together appropriately selected fusion components. FR 1.3.1 Parent component. The parent component, referred to as the base or principal component in previous versions of these rules, is the one with the highest seniority according to the criteria given in FR 2.3 and is represented in the fusion name by that ring or ring system which is cited last in the name. It may be mono or polycyclic. FR 1.3.2 Attached components. The components of a fused ring system which are not covered by the parent component are called attached components and are expressed by fusion prefixes. Prefixes denoting components directly fused to the parent component are called first-order fusion prefixes. The rest are called second-order, third-order, etc. fusion prefixes, which means they correspond to the second, third, etc. component reached when moving away from the parent component across fusion sites. All attached components may be mono or polycyclic. Note: details of the method for naming fused ring systems are not given until FR 4. FR 1.3.3 Interparent components. In a system that consists of two or more parent components, ortho or ortho and perifused to the same attached component, the latter is called the first-order interparent component. Likewise, if two or more parent components are linked by three appropriately attached components, there will be two identical first-order interparent components and a second-order interparent component. Systems with 5 or more interparent components are regarded in a similar way. See FR 6 for the special rules used to name systems with interparent components. FR 1.4 Bridges. An atom or group of atoms is named as a bridge by means of a prefix if it fulfills one or more of the following criteria. A. If it connects two or more non-adjacent positions of the same ring in a fused ring system. B. If it connects two or more positions of different rings of a fused ring system and does not thereby form a new ortho and perifused ring. C. If it connects positions in a ring of a fused ring system to a previously described bridge but cannot be included as part of that bridge. D. If it connects the atoms at the end of a bond common to two rings of a fused ring system. E. If it is necessary to describe a system with only ortho or ortho and perifusions, but which cannot be completely named by fusion principles.
Notes 1. See Rule A31.1 for a different definition of a bridge in a von Baer system. 2. Beilstein uses cyclo to indicate a direct bond between two non-adjacent positions of a fused ring system. For example, the skeleton below is named by Beilstein as 1,5-cycloindene instead of a bridged pentylene. The preferred bridged pentylene has a bivalent bridge. With complex systems, cyclo may facilitate generation of names. For example, FR 8.2.I is illustrated by a system which could be called 3,4-cyclo-2,5-methino dipentyleno 2,1-F 2'1', F', cyclopenta 2,1-A 3,4-A' dipentylene. 3. For the purpose of naming polycyclic fused and bridged fused ring systems, the parent hydride is considered as two-dimensional skeleton with normally the maximum number of non-cumulative double bonds in the fused ring system, for example, excluding the bridges. The exceptions to this situation are when there is a double bond between a bridge and a fused ring system in the structure under consideration, for example, requiring the use of the ending -ylidene, see FR 8.3.2, or when a bridge terminates an existing fusion atom or trivalent atom. In considering alternative ways of naming a bridged fused ring system, the number and location of the double bonds as alternative parent structures may vary. Also, the parent structure, so described, may not exist as such, but only in a hydrogenated or partially hydrogenated form. For example, although all three structures in Node 2 above have the same skeleton, the double bonds of the preferred structure are located differently from the other two, since the maximum number of non-cumulative double bonds is always assigned in the ortho or the ortho and perifused portion. FR 1.4.1 Simple bridged prefix. A simple bridged prefix describes an atom or a group of atoms
that may be considered as a single unit, for example, epoxy, butano, benzeno. FR 1.4.2 Composite bridge prefix. A composite bridge prefix describes a group of atoms that can only be considered as a contiguous sequence of simple bridges. For example, epoxy methano is the same as epoxy plus metheno. It has also been called a compound bridge prefix. FR 1.4.3 Bivalent bridge. A bivalent bridge is one which is connected by single bonds to different positions on a fused ring system or bridged fused ring system. FR 1.4.4 Polyvalent bridge. A polyvalent bridge is one that is connected to a fused ring system by 3 or more single bonds or their multiple bond equivalents. A polyvalent bridge may often be considered as a combination of two bivalent simple bridges, one first order and one the other dependent. Polyvalent bridges may be further classified as bipodal, tripodal, etc., where the bridge is attached to 2 positions, 3 positions, etc.
FR 1.4.5 Independent bridge. A bridge which only connects 2 or more positions of a fused ring system is called an independent bridge. FR 1.4.6 Dependent bridge. A bridge which connects 1 or more positions of a fused ring system to 1 or more positions on a simple or composite independent bridge and cannot be expressed as part of a larger composite bridge is called a dependent bridge. FR 2 Ring systems used as components. The names of polycyclic fused ring systems are derived from those of components which are themselves mono or polycyclic ring systems. FR 2.1 Hydrocarbon components. Hydrocarbon parent components are listed in Appendix 1. The components are listed in decreasing order of preference for choice of components. FR 2.1.1 Monocyclic hydrocarbon components. Monocyclic hydrocarbon parent components other than benzene are named as N-annulenes, where N represents the ring size. The corresponding attached component prefix is derived from the appropriate cycloalkane stem with the ending A. Notes: 1. In previous versions of these rules, the parent components was named from the cycloalkane stem with the ending -ene. This would normally imply 1 double bond in the ring in contrast to the meaning here of the system with the maximum number of non-cumulative double bonds. Use of the N-annulene terminology prevents any confusion. The traditional names of the attached components are retained. 2. N-annuleno is not used as a prefix. 3. The alternative method for the naming of these systems described in Rule A23.5 is abandoned. 4. N-annulene with N smaller 6 is only used as a parent component, not for the isolated system. FR 2.1.2 Polyacene components. A hydrocarbon parent component that consists of 4 or more orthofused benzene rings in a straight linear arrangement is named from the numerical prefix denoting the number of benzene rings followed by the ending acene, derived from anthracene. In an attached component prefix, the ending acene is changed to aceno. Note that tetracene was called naphtacene in Rule A21.1, and this is still used by Kaas and Beilstein. FR 2.1.3 Polyaphene components. A hydrocarbon parent component that consists of N orthofused benzene rings, N bigger 3, and comprises 2 straight linear arrangements of N plus 1 divided by 2 and N plus 1 divided by 2 if N is odd, or N divided by 2 and N divided by 2 plus 1 rings if N is even, with the common benzene rings, and which makes a formal angle of 120 degrees, is named by citing the numerical prefix denoting the total number of benzene rings followed by the ending aphene, derived from phenanthine. In an attached component prefix, the ending aphene is changed to apheno.
FR 2.1.4 Polyalene components. A hydrocarbon parent component that consists of 2 identical orthofused monocyclic hydrocarbon rings is named from the numerical prefix denoting the number of carbon atoms in each ring and the ending -alene. The trivial name naphthalene is retained for hexalene. In an attached component prefix, the ending -alene is changed to -aleno. FR 2.1.5 Polyphenylene components. A hydrocarbon parent component that consists of a monocyclic hydrocarbon with an even number of carbon atoms and benzene rings, orthofused to alternate sides, is named from the numerical prefix denoting the number of benzene rings followed by the ending phenylene. In an attached component prefix, the ending phenylene is changed to phenyleno. As an exception, the first member of the series is called biphenylene instead of diphenylene. FR 2.1.6 Polynaphthalene components. A hydrocarbon parent component that consists of a monocyclic hydrocarbon with an even number of carbon atoms and with naphthalene ring systems 2,3 fused to alternate sides is named from the numerical prefix denoting the number of naphthalene units followed by the ending naphthalene. In an attached component prefix, the terminal E is changed to O. The first member of the series with two naphthalene ring systems is called dibenzo BH biphenylene and is not used as a component. FR 2.1.7 Polyhelicene components. A hydrocarbon parent component of 6 or more rings that consists of a benzene ring fused to the 3,4 position of phenanthine and further benzene rings fused in a similar way is named from the numerical prefix denoting the total number of rings followed by the ending helicene. The numbering of these ring systems using FR5 presents a problem due to ring overlap and that the ring where numbering should start depends on the number of rings present. To circumvent this problem, it is recommended that a terminal ring be numbered from 1 to 4, followed in the nominal way round the external peripheral atoms, followed by the internal peripheral atoms. Note: polyhelicene names are not used in Cas index nomenclature. FR 2.1.8 Acylene components. A hydrocarbon parent component that consists of a 5-membered ring, ortho and peri-fused to naphthalene, anthracene or phenanthine is named by adding the prefix ace and changing the ending alene, acene or ene respectively to ylene. FR 2.1.9 Trivially named hydrocarbon components. The trivially named hydrocarbons used as parent components in fused nomenclature are listed below. The reference numbers refer to the entry in Appendix 1. Anthracene, acylene, benzene, cresene, coronene, fluoranthene, fluorine, as-indocene, S-indocene, indene, naphthalene, overlene, parylene, phenylene, phenanthine, pekene, pleiadene, pyranthene, pyrene, rubicene. In an attached component prefix, the ending -ene is changed to -eno, e.g. pyreno from pyrene. Only the following abbreviated forms are used: anthra from anthracene, benzo from benzene, naphtho from naphthalene, phenanthro from phenanthine. Notes: 1. Rule A21.4 also recommended the abbreviations of asenaphthaleno and peryleno to asenaphto and pyrilo, which are still used by Kaas and Beilstein. 2. The non-standard numberings of anthracene and phenanthine are retained. 3. Kaas and Beilstein also include tridene, cyclopentane E, as-indocene. FR 2.1.9 Trivially named hydrocarbon components. The trivially named hydrocarbons used as parent components in fusion nomenclature are listed below. The reference numbers refer to the entry in Appendix 1.
FR 2.2 Heterocyclic component. Heterocyclic parent components are listed in Appendix 2. The components are listed in decreasing order of preference. FR 2.2.1 Heteromonocyclic components. A. The following trivial names are retained for heteromonocyclic parent components. The reference numbers refer to the entry in Appendix 2. Furan, imidazole, puran, pyrazine, pyrazole, pyridazine, pyridine, pyrimidine, pyrrole, selenophene, tellurofene, thiophene, thiopuran. In an attached component prefix, the terminal E is changed to O, or the O is added in the case of puran and chalcogen analogs. Only the following abbreviated forms are used: furo from furan, imidazo from imidazole, pyrido from pyridine, pyrimido from pyrimidine, thieno from thiophene. These abbreviated forms are also used in combined forms, in example benzofuro. Note 1. In the previous edition of these rules, oxazole, isooxazole, thiazole, and isothiazole were used as component names. When combined in heterobicyclic names with a benzene ring, locants were required for the isocase. The full Hunch-Whitman name is now recommended for fusion names, in example 1,3-oxazole, 1,2-oxazole, 1,3-thiazole, and 1,2-thiazole respectively. The traditional names are retained in these recommendations for use with the isolated ring system and are still used as fusion components by CAS and Beilstein together with selenazole, isoselenazole, tellurazole, and isotellurazole. Note 2. Beilstein uses selenopuran and telluropuran instead of selenine and tellurine. B. A heteromonocyclic parent component with a ring of up to 10 members, not listed in FR 2.2.1a, is named using the extended Hunch-Whitman system. In an attached component prefix, the terminal E is changed to O. In fused ring names, where locants are needed to locate the heteroatoms in a component ring, these locants are cited in square brackets. Notes 1. In the Hunch-Whitman system, the terminal E is optional. In this document, the E is included. If the E is omitted, the terminal EN is changed to ENO. 2. The Hunch-Whitman suffix is that appropriate for a mancute, meaning maximum number of non-cumulative double bonds, ring system. C. A heteromonocyclic parent component with more than 10 members is named by modifying the corresponding heterocycloalkane name, changing the ending -ane to -ine. In an attached component prefix, the terminal E is changed to O. If locants are needed to locate the heteroatoms, these are cited in square brackets. Where there is a choice of locants, they are selected as in the Hunch-Whitman system. Note: when a heteromonocyclic component with more than 10 members is present, Beilstein uses replacement nomenclature.
FR 2.2.2 Heteroanthrene components. A heterotricyclic parent component that consists of two benzene rings fused to a 1,4-dihedrobenzene, in which the heteroatoms are the same, is named from the appropriate replacement prefix and the suffix anthrene with elision of the A. In an attached component prefix, the ending -ene is changed to -eno. Appendix 2 includes the system for oxygen, sulfur, selenium, tellurium, phosphorus, arsenic, silicon, boron, and mercury. The nitrogen analog is an exception and is named phenazine. Boranthrene, oxanthrene, silanthrene, and tellurantrene were not included previously. Oxanthrene is still called dibenzo-1,4-dioxine by Chemical Abstract Service and Beilstein. Mercuranthrene, formerly called phenymercurine or phenymercurine, is called cyclodi-mu-1,2-phenylene dimercury by Chemical Abstract Service. FR 2.2.3 Phenoene components. A heterotricyclic parent component that consists of two benzene rings fused to a 1,4-dihydrobenzene in which the heteroatoms are different is named by adding the prefix pheno to the Hunch-Widman name. In an attached component prefix, the ending -ene is changed into -eno. Appendix 2 includes the system for amines with oxygen, sulfur, selenium and tellurium, nitrogen with phosphorus, arsenic and mercury, oxygen with sulfur, selenium, tellurium, phosphates, arsenes and stibines, and sulfur with arsenes. Phenoxyastibinene was previously called phenoxyantimonine. 2H-phenomyrcurezine, formerly called 2H-phenomyrcazine, is called 3,6-cyclohexadiene, 1-yle-2-ylidine nitrile 1,2-phenylene mercury by chemical abstract service. FR 2.2.4 diazonaphthalene and diazophenanthine components. A heterocyclic component which corresponds to naphthalene or phenanthine, where each terminal ring has one non-fusion atom replaced by nitrogen, is called naphthyridine or phenanthroline respectively. The location of the two nitrogen atoms is indicated by the appropriate locants. See Appendix 2 for the range of isomers possible for naphthyridine and phenanthroline. Note: phenanthroline is numbered in the standard way, despite the non-standard numbering of phenanthine. FR 2.2.5 trivially named polycyclic nitrogen heterocyclic components. The following trivial names of the nitrogen heterocycles are also used as parent components in fusion nomenclature. In an attached component prefix, the terminal E is changed to O, for example indolo from indole. Acridine, carbazole, cinnoline, indazole, indole, indolizine, isoindole, isoquinoline, naphthyridine, pyrimidine, phenanthridine, phenanthroline, phenazine, phthalazine, pteridine, purine, pyrrolizine, quinazoline, quinoline, quinolizine, quinoxaline. Notes: 1. Rule B 3.3 recommended the abbreviation of isoquinolino to isoquino and quinolino to quino. These abbreviated forms are not used here but are still used by Chemical Abstract Service and Ballstein. 2. Beta-carboline, pyrido 3,4-B indole, was abandoned as a component name in 1979. 3. Aquindoline, anthracene, anthyridine, phenanthracene, phthalopyridine, quindoline, quinindoline, thebanidine, triphenodioxazine, and triphenodithiazine are used as component names by Chemical Abstract Service. 4. 1-pyrindine, cyclopenta-B-pyridine, and 2-pyrindine, cyclopenta-C-pyridine, are used by Chemical Abstract Service and Ballstein for the isolated ring system, but not as a component for fusion.
FR 2.2.6 Components formed by replacement of nitrogen by arsenic or phosphorus. The following parent components containing arsenic or phosphorus are named by adaptation of the corresponding nitrogenous parent component names. Nitrogen: acridine, indole, indolizine, isoindole, isoquinoline, phenanthridine, quinoline, quinolizine. Arsenic: acridenzine, arsindole, arsindolizine, isoarsindole, isoarsinoline, arsantridine, arsinoline, arsinolizine. Phosphorus: acridophosphine, phosphindole, phosphindolizine, isophosphindole, isophosphinolene, phosphanthridine, phosphinoline, phosphinolizine. In an attached component prefix, the terminal E is changed to O. FR 2.2.7 trivially named polycyclic chalcogen heterocycling components. The following trivial names of chalcogen heterocyclers are also used in fusion nomenclature: chromine, thiochromine, selenochromine, tellurochromine, isochromine, isothiochromine, isoselenochromine, isotellurochromine, xanthine, thioxanthine, selenoxanthine, telluroxanthine. In an attached component prefix, the terminal E is changed to O. For example, xanthino from xanthine. Note: chromine and isochromine and the chalcogene analogues are not used by Cas but are used by Beilstein. Cas uses 1-benzopyran, 2-benzopyran, etc. FR 2.2.8 Heterobicyclic components with a benzene ring. Unless listed as a trivially named heterobicycle in Appendix 2, a benzene ring fused to a heteromonocycle of 5 or more members, a benzoheterocycle, is named by prefixing number locants, indicating the positions of the heteroatoms to benzo followed by the trivial Hansch-Wittmann or modified replacement name of the heteromonocycle without locants. The locants quoted correspond to the numbering of the bicyclic structure, which follows FR 5.4. Locants are not needed if their omission does not result in ambiguity. For example, benzimidazole, benzotriazole. As an exception to FR 4.7, the O of benzo is elided if followed by a vowel. See FR 3.5 for the use of this type of name as a component, and FR 4.8 for the use of square brackets around locants. Brackets are not used for the unmodified ring system. Names of this type are only used as components under certain conditions. See FR 3.5 for the details. Beilstein does not use this type of name. Note 1. 1-benzopyran and 2-benzopyran were formerly called benzopyran and isobenzopyran, and may still be used for the isolated ring system. Cas still uses benzopyran and isobenzopyran as fusion components. 2. 1,2-benzoxazole and its 2,1 and 1,3 isomers and chalcogen analogues were called 1,2-benzisoxazole, 2,1-benzisoxazole, benzoxazole, etc. These are still used by Cas for the isolated ring system and as fusion components.
FR 2.3 Priority Order of Component Ring Systems. Selection of a parent component or attached component is based on the following rules, which are applied in order. Appendices 1 and 2 list the hydrocarbon and heterocyclic components in decreasing order of preference. If there is a choice, the preferred component should be A heterocyclic component containing the heteroatom occurring earliest in the order nitrogen, fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium, tellurium, phosphorus, arsenic, antimony, bismuth, silicon, germanium, tin, lead, boron, mercury. See Table 1 of the revised Hansch-Wittmann system. B. A component containing greater number of rings. C. A component containing the larger ring at the first point of difference when comparing rings in order of decreasing size. D. A component containing the greater number of heteroatoms of any kind. E. A component containing the greater variety of heteroatoms. F. A component containing the greater number of heteroatoms most preferred when considered in the order of fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium, tellurium, nitrogen, phosphorus, arsenic, antimony, bismuth, silicon, germanium, tin, lead, boron, mercury. See Table 1 of the revised Hansch-Wittmann system. G. A component in the preferred orientation according to FR 5.2. H. A component with the lower locants for heteroatoms. Note: quinoline is an exception to this rule in Cas, where it is preferred to quinoline or isoquinoline. I. A component with the lower locants for the heteroatoms when considered in the order fluorine, chlorine, bromine, iodine, oxygen, sulfur,
selenium, tellurium, nitrogen, phosphorus, arsenic, antimony, bismuth, silicon, germanium, tin, lead, boron, mercury. See Table 1 of the revised Hans-Wiedmann system. J. A component with the lower locants for bridgehead carbon atoms. FR 2.4 Natural products and fullerenes. Fusion of components to natural products and fullerenes are not included in this document. Details have been published for carbohydrates, steroids, and tetrapyrols, and there are proposals for prostaglandins, thromboxanes, natural products in general, and fullerenes. FR 3 Construction of fusion names. FR 3.1 Ortho or ortho and perifused systems. Before naming a polycyclic parent hydride containing a fused ring system, it is necessary to identify the bridges, if any, which are treated separately from the ortho or ortho and perifused system. FR 3.2 Selection of components. Each ring and/or combination of rings in a fused ring system is considered in order to select the parent component. The first order attached component is then selected, if necessary, followed by the second order attached component and higher order attached components. It should be noted that when a heteroatom is common to two components, it must be indicated in the name of each component. If an atom is in a non-standard valence state, this is indicated using the lambda convention. The bonding number n is cited as a superscript, that is lambda n, together with the locant of the atom with a non-standard valence state, in front of the name of the fused ring system. Note: fusion nomenclature provides no means of describing the fusion of one component to two other components which are themselves fused together. If this problem arises, see FR 7 for examples and how to name them.
FR 3.3 Selection of parent components. The ring or rings selected as the parent component are those most preferred by the criteria of FR 2.3. The parent component may be identified in more than one location in a fused ring system by using different rings or combinations of rings. Such alternative locations of the parent component may be overlapping or directly fused together or separated by one or more components. When there are alternative locations for the parent components, the criteria of FR 3.3.1 are used to select the preferred locations. FR 3.3.1 Order of preference between locations for parent components. If there are two or more potential locations for a parent component, the following criteria apply in order until the distinction is obtained. If a partial distinction is obtained, the following criteria are only applied to distinguish between remaining choices. A. The location that enables the whole ring system to be named by fusion nomenclature is preferred to one where alternative approaches are required. Note: with this criterion, CIS and Beilstein permit the use of a less preferred parent component or attached component if that enables the whole system to be named by fusion nomenclature. B. The location that results in a name which does not require high-order attached components. C. The location that results in a maximum number of first-ordered attached components, then second-order, etc. D. A location that permits the expression of the maximum number of identical attached components with multiplicative prefixes. E. A location that uses the preferred interparent component. F. A location that results in preferred attached components comparing first-order attached components, then their attachment locants, then comparing the preferred second-order attached components in order of the priority of the first-order components to which they are attached, then their attachment locants, then third-order components, etc. FR 3.4 Selection of attached components. After selection of the parent component or parent components and interparent components, if a multiparent name is selected, other rings are identified as far as possible as attached components. If there are alternative first-order attached components, FR 2.3 is used to select a preferred component. If there are alternative locations for the first-order attached components, the criteria of FR 3.4.1 are used to select a preferred arrangement. After selection of the first-order attached components, remaining rings are considered for second-order attached components and so on to higher-ordered attached components. If there are alternative names which only differ in their fusion locants, see FR 4.5 for the criteria to select the preferred name. Note: heterobicyclic components with a benzene ring named by FR 2.2.8 are only identified after this stage.
FR 3.4.1 Order of preferences between attached compounds. If after consideration of the parent compound there are two or more potential attached compounds, or two or more locations for an attached compound, the following criteria are applied in order until destruction between remaining choices. The location that has preferred locants for fusion to the parent compound as a set. B. The location that has preferred locants for fusion to the parent compound in order of situation. C. The above produced is considered exploring outwards to the preferred second-order attached compound. Preferred fusion locants between the first and the second-order attached compound. FR 3.5 Heterobicyclic compounds with a benzene ring as a component. If the intentionally identified preferred compounds for naming the fused ring system include an acylatic benzo compound, not forming part of a compound such as quinoline or naphthalene, or to fuse to a heteromonocyclic compound, these two components are treated together as one component unit, a benzoheterocycle. However, this approach should not be used if it disrupts a multi-parent name or the use of multiplicative prefixes. The other intentionally identified preferred component should not be changed in any other way except insofar as the benzoheterocycle component may change the order of the attached components and may affect the choice of the preferred parent and or attached component. Fusion between two components is identified by the technique described in FR4. All attached components are seated in front of the parent compounds. Each second-order attached component is seated in front of the first-order attached component to which is fused and so on higher-order attached components. If there are two or more different compounds or set compounds attached to low-order compound, they are seated in alphabetic order. If the only destruction is between A-S indicane and S indicane, then the italic characters are considered, otherwise they are treated as indicane for consideration of alphabetic order. If two or more identical compounds are fused to a third, they are seated together by use of D or tri, or bis or tris, as described in FR 4.9. Use of a multiplicative prefix does not affect the alphabetic order of the citation of compounds attached at the same level. If two or more groups of compounds only differ by virtue of the fusion locants within the group, they are used to determine the order. If two or more groups compounds only differ by virtue of the heteroatom locants, they are used to determine the order.
FR4 Fusion descriptors. After identification of components, the fusion name can be constructed. Details of how the common bonds are specified are given below. Examples are labeled where appropriate with the relevant letters or locants of components within the rings and with the numbering of the whole ring system outside the structure. FR 4.1 Identification of sites of parent components. The sites around the periphery of the parent component are identified by italic letters A, B, C, etc. with a A for the site 1, 2, B for the site 2, 3, or in certain cases 2, 2, A, for example, azonaphthalene, etc. Following continuously round the periphery, ignoring non-standard numbering. If there are more than 26 sites, the additional sites are identified by subscript numbers A1, B1, C1, etc., then A2, B2, C2, etc. Contrast to the use of A', B', C', etc. in FR 6.1.
Each letter locant implies also a direction for the specified bond, i.e. the direction of the side A is from the atom with locant 1 to the atom with the next higher locant. FR 4.2 Identification of sites of attached components. The sites of attached components are identified by the appropriate pairs of number locants. FR 4.3 Fusion of a first-order attached component to the parent component. Those bonds that are common to each component are indicated by the appropriate numerical locants for the attached components and letter locants for the parent component separated by a hyphen and cited within square brackets. Numerical locants are separated by commas, while letter locants are quoted together if there is more than one. Letter locants are cited in the same direction as they were assigned. The numerical locants are cited in the same direction as the letter locants. The first-order attached component is quoted before the locant set to which it applies and in front of the parent component name. If there is more than one first-order attached component, they are quoted in alphabetical order unless second-order attached components modify this order. See FR 4.6 for the omission of locants. FR 4.4 Fusion of a higher order component to an attached component. The procedure for indicating the common bonds between a higher order attached component and an attached component follows that for the attachment of the first order attached component to the parent component, except that only numerical locants are used instead of letters and the two sets of locants are separated by a column. The locants of second-order attached components are primed to contrast with those of first-order attached components. The locants of third-order, fourth-order, etc. attached components are double, triple, etc. primed. If more than one component is fused to the same lower-order component, they are cited in alphabetical order unless higher-order components alter this order.
FR 4.5 Choice of locants. If there is a choice of numerical or letter locants consistent with the numbering of the component, then the lower numbers or letters are selected. Preference is given in the following order. A. Parent component letters as a set. B. Parent component letters in order of citation. C. Set of locants for the first order attached components for fusion to the parent component. D. First order attached component locants for fusion to the parent component in order of citation. E. Locants for lower ordered attached components as a set for fusion to higher order attached components. F. Locants for lower ordered attached components for fusion to higher order attached components in order of citation. G. Locants for higher order attached components as a set for fusion to the lower order attached component. H. Locants for higher order components for fusion to lower order components in order of citation. FR 4.6 Omission of locants. FR 4.6.1 Unnecessary locants. If there is no ambiguity, the numerical and/or letter locants may be omitted for a system with only first-order attached components. Locants are also omitted when there is no ambiguity for the fusion of terminal attached components. When locants are required for the fusion of a higher-order component, then all locants for the linking component must be cited. FR 4.6.2 Locants of peripheral fusion carbon atoms of a component. The numerical locants of peripheral fusion carbon atoms of a component are omitted with an ortho and peri-fused system. Both terminal fusion atom locants for ortho fusion must be cited even if one is a fusion atom. FR 4.7 Elision. Vowels are not elided in fusion names, However, see FR 2.2.8. Note: the previous edition of these rules included elision, which is still used by CAS in the following way. When as a naphtho, benzo, or naphtho is followed by a component which starts with a vowel, the O is elided. Similarly, the A of cycloalkyl is elided under these conditions. In all other cases, the O or A is retained. If there is more than one first-order attached component and at least one second-order attached component, elision between the second-order and the first-order attached component is applied after determination of the alphabetical order of the components. FR 4.8. Heteroatom locants of components. When a component requires the citation of locants, e.g. in a Hans-Schwiedmann name, these are always quoted in square brackets. Note that these numbers in brackets only refer to the numbering of the component and have no significance in the final numbering of the complete fused ring system. Note: in the previous version of these rules, any locants of a component which are cited in the name and are the same as that of the final system are not enclosed in brackets. CAS still does not use brackets when the locants of the heteroatoms of the component correspond to those of the whole fused ring system.
FR 4.9. Treatment of identical attached components. When there are two or more components which are identical and both fused to a parent or attached component, this is indicated by the use of the prefix di, tri, etc. or bis, tris, etc. to avoid ambiguity. This multiplicative prefix is not considered in deciding the alphabetical order of components attached at the same level. If a complete set of locants are used for first-order attached components fused to the parent component, these are cited together separated by a colon. If abbreviated sets of locants are used, the letters are separated by a comma. If complete sets of locants are used for second-order attached components fused to a first-order attached component, or for higher-order cases, the locants are cited together separated by a semicolon. If abbreviated sets are used, they are separated by a colon. To distinguish between the two or more components of the same order, the locants of the second component are primed, or double primed if the first is primed, etc. The third double primed, etc. If the use of di, tri, etc. might be ambiguous, bis, tris, etc. are used. This applies when di, tri, etc. prefixes might be used to name the component, e.g. Hans-Schwiedmann name. Note 1. Apart from the use of a hyphen with a full set of locants for fusion of the first-ordered attached component to a parent component, the punctuation is in the order comma, colon, semicolon. The semicolon separates sets which use a colon. The colon separates sets which use a comma or hyphen, and the comma is used only if one punctuation mark is needed. Beilstein uses the hyphen as above. A colon is used for fusion of attached components. A semicolon is used to separate fusion descriptors which already contain a colon or comma, e.g. diforo 32b, 3'4'e pyridine and dibenzo 4,5,6,7 cycloocta 1,2-C furan. FR 4.9.1 Additional components attached to a system with a multiplicative prefix. Fusion of a higher order attached component to a system named with a multiplicative prefix requires each set of attached components to be specified separately. FR 4.9.2 Groups of identical components with identical fusion. When two or more groups of identical components, including identical fusion between these components, are fused to another component, this is indicated by the use of bis, tris, etc., with a group of components in round brackets. FR5 Numbering. The older rules for numbering fused ring systems were based on the concept of converting all systems into an approximate two-dimensional hexagonal grid framework. As the complexity of fused ring systems increased, these arbitrary rules have been extended as needed. It is recognized that there are problems which are not covered by this document with some systems containing 3-membered rings or with rings greater than 7. Note: all ring systems in this document have been drawn so that the peripheral numbering, not always shown, is clockwise and starts approximately in the top right-hand ring.
FR 5.1 Drawing of fused ring systems for orientation. Before the fused ring system can be orientated, it must be drawn according to the following specifications. If more than one drawing meets these specifications, the one chosen is that which gives the more preferred orientation, and if there is still a choice, the more preferred numbering. FR 5.1.1 Allowable shapes for component rings in the horizontal row. In the preferred orientation of a ring system, as many rings as possible should be in the same horizontal row. The 5-membered ring may be considered as a 6-membered ring with one atom eliminated and replaced by an elongated bond. Rings with an even number of members greater than 6 are considered as modified 6-membered rings with additional pairs of horizontal bonds inserted between the two halves. This arrangement ensures that rings fused on both sides in the horizontal row are fused to bonds as far apart as possible. A ring with an odd number of members greater than 6 is considered as a modification of the corresponding even-membered ring with one more or less above or below, so that rings fused on both sides in the horizontal row are fused to bonds as far apart as possible. The 3 left-hand forms correspond to insertion into a smaller ring with one less member. The 2 right-hand forms correspond to deletion from larger rings with one more member. In each case, the rings may also be orientated with the modified region at the top instead of the bottom. FR 5.1.2 Allowable shapes for other component rings. Rings ortho or ortho and perifuse to the horizontal row may also be drawn as shown in FR 5.1.1. but other shapes or orientations are permitted. Additional modifications of rings with more than 7 members are permitted. These modifications may be required for fusion to the horizontal row, or if additional rings are fused above or below the 9 or 10-membered rings, they may need to be used for rings in the main horizontal row provided the rings on either side in the horizontal row are fused to bonds as far apart as possible, i.e. to the bond with a dot at each and for a 10-membered ring. In drawing an ortho and perifusion, the individual rings should be orientated so that each internal ring angle involved is 120 degrees. If this is not possible, see FR 5.1.5. Elongated bonds should not be used for fusion. If this is not possible, see FR 0.1.6. FR 5.1.3 Overlap of bonds. If the fused ring system can be drawn in more than one way using the preferred ring shapes, preference is given to those forms which do not involve overlap of bonds. If, when using these preferred ring shapes, 2 bonds overlap, it is necessary to draw one or both of the rings involving those bonds with a modified shape to show that the two rings are not ortho-fused together. This modification is not considered to represent distortion in the sense of FR 5.1.5. FR 5.1.4 Overlap of rings. If the fused ring system can be drawn in more than one way using the preferred ring shapes, preference is given to those forms which do not involve overlap of rings. If, when using these preferred ring shapes, two rings overlap, it may be necessary to draw one or more rings with a slight modification to show the two overlapping rings. This modification does not constitute distortion in the sense of FR 5.1.5.
FR 5.1.5 Distorted ring shapes. If the fused ring system cannot be drawn using only the above shapes, then the minimum number of distorted ring shapes should be used. Where there is a choice, distortion of a smaller ring is preferred to distortion of a larger ring. If possible, the rings in the horizontal row should not be distorted. The 100-degree angles marked with an X are suitable for perifusion. The thickened, elongated bonds should not be used for fusion. FR 5.1.6 Fusion to an elongated bond. If the fused ring system cannot be drawn following FR 5.1.1, FR 5.1.2 or FR 5.1.5, then the minimum number of elongated bonds may be used for fusion. If there is a choice, then the elongated bonds of a smaller ring are preferred to those of a larger ring. FR 5.2 Orientation. Before the drawing or drawings, if there is more than one of equal preference, is numbered, it needs to be orientated. In considering possible orientations, it should be remembered that the system can be rotated in the plane of the ring system and can also be turned over. The preferred orientation is established by consideration of the following points in order. If a choice remains, then the final decision is made by consideration of the preferred numbering. A. Maximum number of rings in a horizontal row. The preferred drawing is that with the greatest number of orthofused rings, with vertical common bonds in a horizontal row. The relevant vertical bonds are always those furthest apart. If the correct orientation is not immediately apparent, bisect the horizontal row for a horizontal axis and a vertical axis to form 4 quadrants. Rings which are bisected by the horizontal axis but are not directly orthofused to the main row are not considered when counting how many rings are in the row. B. Number of rings in the upper right quadrant. In the preferred orientation, the maximum number of rings should appear above the horizontal row on the right-hand side, thus in the upper right quadrant. For this purpose, the center of the row is defined as the central common bond, if there's an even number of rings in the row, and the center of the central ring if there's an odd number of rings. When counting rings in a quadrant, those rings which are divided by an axis are considered as 2 halves, and the ring at the center of the row, if bisected by both axes, counts as 4 quarters. C. Minimum number of rings in lower left quadrant. In the preferred orientation, the minimum number of rings should appear below the row on the left-hand side, in the lower left quadrant. D. Maximum number of rings above the horizontal row. In the preferred orientation, the maximum number of rings should appear above the horizontal row, identified in FR 5.2. The preferred orientation is that which gives the preferred peripheral numbering.
FR 5.3 Peripheral numbering. The numbering of the peripheral atoms in a particular orientation starts from the uppermost ring. If there is more than one uppermost ring, the ring furthest to the right is chosen. Numbering starts from the non-fusion atom most counterclockwise in the ring selected, and numbering proceeds in a clockwise direction around the system, including fusion heteroatoms. Fusion carbon atoms are not included. Each fusion carbon atom is given the same number as the immediately preceding position, modified by a Roman letter A, B, C, etc. If heteroatoms are identified by replacement nomenclature, all atoms retain the numbers of the parent hydrocarbon. Note: polyhelicines are treated differently as an exception to this rule. If they are rings of different sizes, consideration of the uppermost ring is based on the level above the horizontal row of FR 5.2a in the idealized two-dimensional hexagonal grid rather than the geometric height above the horizontal row. Rings directly fused to the horizontal row identified in FR 5.2a are considered as the first row above the horizontal. The second row above are fused to the first row, and so on. If due to overlap there is still a choice, the ring fused to the ring furthest right is chosen. If there is a choice of starting points, numbering starts from the atom most counterclockwise in the continuous non-fusion portion of the ring selected. If there is still a choice of starting points, the uppermost one is selected. If the selected ring does not have a non-fusion atom, then numbering starts in the next ring and counted when proceeding round the system in a clockwise direction. FR 5.4 Order of preference between alternative numbering systems. If there are alternative orientations of a ring system which are equally preferred after the application of FR 5.2, including alternative locations for the heteroatoms, then the following rules are applied in order until a preferred numbering of the peripheral atoms is identified. A. Give low numbers for the heteroatoms as a set. B. Give low numbers for heteroatoms when considered in the order oxygen, sulfur, selenium, tellurium, nitrogen, astatine, antimony, bismuth, silicon, germanium, tin, lead, boron, mercury. That means Table 1 of the revised Hansch-Widman system. C. Give low numbers to fusion carbon atoms. D. Give low numbers to fusion rather than non-fusion atoms of the same hetero element. E. Give low numbers so that an internal heteroatom is nearer. That means less bonds in the pathway to the lowest numbered fusion peripheral atom. F. Give low numbers to indicated hydrogen atoms.
FR 5.5 Interior Numbering. FR 5.5.1 Heteroatoms. Interior heteroatoms, not identified by replacement nomenclature, are numbered as the peripheral atoms continuing the number sequence. If there is a choice, the shortest path of bonds from each heteroatom to the periphery is determined. The lower number is given to the heteroatom which is closest to the lowest number peripheral atom. Note: previously it was recommended that the interior heteroatoms were numbered last following the shortest path from the highest previous number. FR 5.5.2 Carbon atoms. Interior carbon atoms are numbered by identifying the minimum numbers of bonds linking them to the periphery. The locant for the interior atom is that of the peripheral atom with a superscript number corresponding to the number of bonds between the two atoms. Note: Rule 822.2 recommended that the interior atoms follow the highest number peripheral atom sequence. If there is a choice of interior atom locants, lower numbers are preferred. A non-free spiro-peripheral atom is not used as a reference for interior carbon atoms, if ambiguity would result. In the first example below, carbon atom 3A is a non-free spiro-peripheral atom. The system described in 822.2 has been developed by CAS to deal with complex examples. The additional rules to number interior atoms for complex examples are as follows. A. Starting from the highest number atom, peripheral atom or interior numbered heteroatom, the longest continuous path of the interior atoms is determined and numbered by adding the letter A, B, C, etc. in turn to that of the highest numbered atom. This procedure is repeated and the next highest number atoms, etc., until all interior atoms are numbered. B. If there are alternative pathways, the two alternative atoms at the branch point are compared using the shortest path to the periphery for each atom. The atom linked in this way to the lowest numbered peripheral atom is selected. C. Isolated interior atoms and chains not covered by A or B above are numbered using the longest chain of unnumbered atoms with the numbering continuing from the highest numbered alphanumeric locant available. D. If there are interior numbered heteroatoms, The longest chain of interior atoms attached to the interior heteroatom is numbered as above. FR6 multi-parent systems. When there are two or more non-overlapping locations for the parent component, and there are author or author and peri fused to the same first-order interparent component, they are treated as multi-parent system and given a multi-parent name. Similarly, a system with 3, 5, 7, etc. interparent components is treated as an extended multi-parent system. Each pair of second or higher or interparent components must be identical. FR 6.1 multi-parent systems with one interparent component. The multiple occurrence of the parent components in a multi-parent system is indicated by the use of the prefix d, tri, etc. or bis, tris, etc. To distinguish between the parent components, the second one has primed letters, the third double primed, etc. And the sets of locand are separated by a colon.
FR 6.2 Additional attached components. Additional attached components may be fused to any of the components of a multiparent system. If FR 4.5 does not provide the preferred locants, preference is given to the unprimed component and the fusion letters are assigned with a lower letter used for fusion to the connecting component. Great care is needed with the use of primes, double primes, etc. to ensure that there is no ambiguity. Thus, additional components fused to the interparent components are cited next to the prefix for this interparent component. Thus, additional components fused to the interparent components are cited next to the prefix for this interparent component. FR 6.3 Multiparent system with 3 or more interparent components. If 2 or more possible parent components are separated by an odd number of interparent components, and these are ordered symmetrically with respect to their component rings, but not necessarily with respect to their fusion locants, the whole system is treated as a multiparent system. Second and higher ordered interparent components are named using the prefix d, tri, etc. or bis, tris, etc. if appropriate. Note: this alternative method of naming symmetric systems is not used by CAS. Beistand applies it to the system with 5 or more interparent components. FR 7 3 components ortho and para fused together. The fusion principles described above only apply between pairs of components. It is not possible to name a system where a third component is ortho and para fused to 2 components which are themselves ortho and para fused together. To avoid this situation, the following procedures are applied in order until a name can be formed. However, if one of the 3 components is a benzene ring and another is a heteromonocycle, then application of FR 2.2.8 will sometimes permit normal fusion procedures that would not otherwise be possible. FR 7.1 Use of replacement nomenclature. If the corresponding hydrocarbon fused ring system can be named by fusion principles or has a trivial name, then the heteroatoms are identified by replacement nomenclature using A terms. FR 7.1.1 Use of less preferred parent component. If the corresponding hydrocarbon fused ring system cannot be named by the fusion principles outlined above, then a less preferred parent component is selected, which will permit fusion nomenclature to be used. FR 7.2 Use of bridging nomenclature. If the fused ring system cannot be named on the basis of normal fusing nomenclature or the use of replacement nomenclature with a corresponding hydrocarbon, or even when using a less preferred parent component, then it is treated as a bridging fused system. The fused ring portion should be selected using FR 8.2.
FR 8 Bridged fused ring systems. FR 8.1 Procedure for naming bridged systems. This section provides an outline of the procedure for naming bridged polycyclic fused ring parent hydrides. FR 8.1.1 Selection of bridge. In a polycyclic skeleton cannot be completely named as a fused ring system, then possible ways of naming the skeleton as a bridged fused ring system are considered. The bridge is selected as described in FR 8.2 to give the preferred fused ring system. FR 8.1.2 Naming of ortho or ortho and perifused portion. The skeleton of the portion of the structure which remains after removal of the bridge is named following FR4. Note that the maximum number of non-cumulative double bonds is assigned after insertion of the bridge. Hence, in order to allow for the necessary free valencies to the bridge, the fused ring system may differ from the isolated fused ring system in the number of non-cumulative double bonds and/or the need for indicated hydrogen. If needed, indicated hydrogen is used to identify the required isomer. FR 8.1.3 Order of citation of bridges. Bridges are cited by the technique described in FR 8.4. If there is more than one independent bridge, they are cited in alphabetical order unless identical. Dependent bridges are cited in front of all independent bridges. If there is a choice of attachment locants, see FR 8.4.3. FR 8.2 Selection of fused ring system to be bridged. The bridge is selected, which results in the preferred fused ring system remaining by the following criteria applied in order. A. The fused ring system before bridging containing the maximum number of rings. B. The fused ring system including the maximum number of skeletal atoms. C. The arrangement having the minimum numbers of heteroatoms in the fused ring system. Note, Cass and Beilstein preferred the heteroatoms in the fused ring portion. D. The most preferred fused ring system according to FR 2.3 applied to the whole fused ring system. E. The number of composite bridges being minimized. F. The number of dependent bridges being a minimum. G. The number of atoms in dependent bridges being a minimum. H. The number of bivalent bridges being a maximum. Similarly, ylylidine is preferred as a trivalent bridge to triyl, etc. In example, diyl is preferred to ylylidine, triyl, diylidine, diylylidine, or tetrayl, etc. i.e., diyl is preferred to ylylidine, triyl, diylidine, diylylidine, or tetrayl, etc. I. The location of bridges which results in the preferred attachment locants, firstly for the independent bridges, then for the dependent bridges. J. The fused ring system which gives the lowest locants for the principal characteristic group. K. The fused ring system being chosen which includes the maximum number of non-cumulative double bonds.
FR 8.3 Naming bridges. FR 8.3.1 Simple bivalent bridges. A. An acyclic bivalent hydrocarbon bridge is named as a prefix derived from the corresponding hydrocarbon name by changing the final E to O. The locant of a double bond, if present, is indicated in square brackets between the hydrocarbon prefix and the ending -eno. If there is a choice, low numbers are preferred. For example, probe 1 eno rather than probe 2 eno. Note that this is not the locant used in the final numbering of the bridged fused ring system. B. A monocyclic hydrocarbon bridge, other than benzene, is named by the same prefix as that used as a fusion prefix. To distinguish between the two, the prefix for a bridge has EP added in front of the name. The bridge is assumed to have the maximum number of non-cumulative double bonds consistent with the attachments of the fused ring system or to other bridges. The positions of the free valencies are indicated by the relevant locants in square brackets directly in front of the bridge name.
Note that these locants are not those assigned to the final structure. C. Any other cyclic hydrocarbon is named as a prefix derived from corresponding unsaturated hydrocarbon name in Appendix 1 by replacing the terminal E by O. If the name of the bridge is the same as the fusion prefix, the bridge is indicated by adding EP in front of the name. The I is elided if followed by a vowel. Locants are used in the same way as in section B. D. An acyclic heteroatom bridge is named by the appropriate prefix. Non-standard valence states are given use the gamma convention. Note: Cas names, hydrocarbons, and non-nitrogenous heterocyclic systems with epimeno bridges by use of the suffix -imine preceded by the appropriate locants with a lesion of a final E if present. E. A heterocyclic bridge is named as a prefix derived from the corresponding heterocyclic compound listed in Appendix 2 by adding an O with a lesion of a final E if present. If the heterocyclic system requires the citation of locants, these are given in square brackets in front of the name. If the name of the bridge is the same as the fusion prefix, the bridge is indicated by adding EP in front of the name. The I is elided if followed by a vowel. FR 8.3.2 Simple polyvalent bridges. Polyvalent bridges are cited within round brackets. Note: brackets are not used by Cass or Beilstein. A. A polyvalent bridge consisted of one atom, other than hydrogen, is named by the appropriate prefix. B. A polyvalent polyatomic bridge is named as the appropriate polyvalent group. If necessary, the positions of the free valencies are indicated in the appropriate locants directly in front of the associated ending. The ending -ilidine is restricted to those cases where there is a double bond between the bridge and the fused ring system. If there is a choice of numbering of the bridge, preference is given to low numbers for A. -il, B. -ilidine, C. double bonds. Note: the previous edition of these rules also used -ilidine to indicate bonds to 2 different positions, and -ilidine to indicate bonds to 3 positions, and cited the locants nearest to the hydrocarbon or numerical prefix in front of that prefix. This practice is still used by Cass. FR 8.3.3 Composite bridges. Composite bridges are named by combining the names of 2 or more simple bridge prefixes. However, see FR 8.5 for a different treatment when the fused ring system is named using replacement nomenclature. Unless cited first, epi is omitted. These prefixes are cited without elision in order starting from the preferred terminal prefix based on the following criteria applied in turn until the decision is reached. A. The simple bridge containing the preferred heteroatom. B. The simple bridge containing the preferred ring system. C. The simple bridge containing the longer acyclic chain. D. The simple bridge which occurs first alphabetically. Composite bridges are cited within round brackets. Locants associated with a cyclic bridge component are cited in attachment order. If an acyclic bridge component requires internal numbering, it is numbered in the direction implied by the bridge name. Acyclic bridge components in a composite bridge are only attached to other components through terminal positions, like only 1 and 3 of propane 1,2,3 trial. If polyvalent acyclic bridge components are used, care must be taken to check that there is no ambiguity. If there is ambiguity, then alternative arrangements such as a dependent bridge must be considered. FR 8.3.4 Elision. Vowels are not elided for bridges. Cas elides the terminal A of a monocyclic hydrocarbon bridge when followed by a vowel. With composite bridges, the terminal O of benzeno or an acyclic component is elided when followed by a component of the composite bridge which starts with a vowel. Iminoetheno is an exception. In all other cases, a terminal A, E, or O is not elided.
FR 8.4 Naming of bridged fused ring systems. FR 8.4.1 Order of citation of bridges. If there is more than one bridge, they are cited in alphabetical order unless one is dependent on another. See FR 8.7.a. In this case, the dependent bridge is cited in front of all independent bridges. Identical bridges of the same order are quoted using the appropriate multiplicative prefix. FR 8.4.2 Attachment locants. The fused ring system is numbered in the usual way. A. Symmetric bridges. The locants of the positions on the fused ring system to which the bridge is attached are cited in numerical order in front of the bridge. B. Asymmetric bridges. The locants of the positions on the fused ring system to which the bridge is attached are cited in the order implied by the name of the asymmetric bridge. Locant order for the three valencies of the bridge is given by FR 8.3. If there is a choice, locants are cited in numerical order. See FR 9.3.2 for the use of indicated hydrogen. FR 8.4.3 Choice of attachment locants. If there is a choice of attachment locants after the application of FR 8.4.2, preference is given in the following order. A. The lowest set of locants for all the bridge attachment points considered as a set. B. Lowest locants in the order of citation for the bridges. Note: Kess and Ballstein select when there is a choice of attachment locants those which result in a lower numbers of heteroatoms in preference to the above criterion. See FR 8.6 for numbering of bridge atoms. Note: See FR 9.3.2 for the use of indicated hydrogen and FR 8.6 for numbering of bridge atoms. FR 8.4.4 Treatment of identical bridges. When there are two or more identical bridges, this is indicated by the use of D, tri, etc. with single bridges, or bis, tris, etc. with composite bridges, or if D, tri, etc. won't be ambiguous. The locants of the bridges are separated by a colon. FR 8.5 Bridged fused ring systems where replacement nomenclature is used. If the fused ring system can only be named using replacement nomenclature, any heteroatoms in a bridge are also named using replacement nomenclature. The replacement terms are cited in front of the name of the corresponding hydrocarbon bridge fused ring system. Note: Kess and Ballstein used the appropriate bridge name, which includes the heteroatom, and replacement prefixes are needed to name the fused ring system. Kess cites the bridge prefixes before replacement prefixes, whereas Ballstein cites replacement prefixes before bridge prefixes. FR 8.6 Numbering of bridge atoms. Bridge atoms are numbered continuing from the highest locant of the fused ring system. If there is more than one bridge atom, excluding hydrogen, the numbering starts at the chain end or the ring atom connected to the bridgehead possessing the highest number. With a composite bridge, each component of the composite bridge is completely numbered before the text component.
If there is a choice of numbers, then preference is given in the following order to A. Low locants for heteroatoms, B. Low locants for bridgehead atoms within a bridge, C. The remaining atoms, excluding hydrogen, being numbered continuously. FR 8.7 Order of numbering bridges. A. Independent bridges are numbered before dependent bridges. B. If there is more than one bridge of the same order, preference is given to the bridge attached to the bridgehead with the higher locant at the first point of difference. C. If two bridges are attached to the same bridgehead atoms, they are numbered in alphabetical order.
FR 9 Indicated hydrogen. FR 9.1 Maximum number of non-cumulative double bonds. The names of polycyclic fused ring systems are considered to correspond to the compound with the maximum number of non-cumulative double bonds, consistent with the appropriate valency of the skeletal atoms. If non-standard valence states are present, this must be indicated using the lambda convention, and if necessary, the gamma convention. The corresponding valency is used in assigning the non-cumulative double bonds. With bridge systems, the assignment of non-cumulative double bonds to the parent fused ring system is applied after allowance for the bonds existing between the bridges and the fused ring system. Rings which form part of a bridge are treated separately, after consideration of free valencies implied by the name. FR 9.2 Localized double bonds. If it's necessary to identify isomers which differ only by virtue of the location of localized double bonds, this is indicated by the use of Greek letter delta. The locants cited correspond to the lowest number atom of a localized double bond. FR 9.3 Citation of indicated hydrogen. When a name applies equally to two or more isomeric systems with a maximum number of non-cumulative double bonds, and when the name can be made specific by indicating the position of one or more hydrogen atoms in the structure, this is accomplished by modifying the name with a locant, followed by an italic H for each of these hydrogen atoms. These atoms are called indicated hydrogen. Notes: 1. Indicated hydrogen is often omitted for the normally encountered isomer of some ring systems. For example, carbazole, fluorine, imidazole, indazole, indene, indole, isochromine, isoindole, pyrimidine, phenylene, phenothiazine, phenoxazine, purine, pyrazole, pyrrole, selenoxanthine, telluroxanthine, dioxanthine, xanthine. 2. Indicated hydrogen might be omitted when there is no ambiguity, for example, at a position located between two divalent atoms. FR 9.3.1 Ortho or ortho and perifuse ring systems. If indicated hydrogen is needed, it is identified by the locant of the relevant position, cited in front of the name of the whole ring system, including replacements terms, if used. FR 9.3.2 Bridge systems. If indicated hydrogen is necessary to distinguish between isomers of the fused ring system and of the bridge, indicated hydrogen is cited in front of the name. The previous edition of these rules separated the indicated hydrogen needed for a bridge from that used for the fused ring system. This system is still used by CAS, who will also use it in, for example, 3A6-ethano 3AH indene, but not with the bridge 2-pyrrolyl 5-ylidine. FR 9.4 Partially hydrogenated fused ring system. Certain partially hydrogenated fused ring systems are named separately. These should not be used as components in fusion nomenclature. The following names are retained: chromane, indane, indoline, isochromane, isoindoline, selenochromane, selenoisochromane, tellurochromane, telluroisochromane, thiochromane, thioisochromane. In the previous edition of these rules, several other examples were listed. For example, asenaphtine, colantrine, aceantrine, acefenantrine, violantrin, isoviolantrin. These are no longer recommended. Waldstein uses all of these except indolin, isoindolin, violantrin, and isoviolantrin. None are used by CAS. The system for naming partially hydrogenated hydrocarbon fused ring systems in Rule 8.23.5 is abandoned.